Tanzania, 1963. A 13-year-old named Erasto Mpemba is making ice cream in a school cooking class. The recipe says cool the boiling mix before you freeze it. But the freezer is filling up fast, so Mpemba shoves his in while it is still hot. An hour later, his is frozen solid. His classmates, started cold, are still slushy. He asks his physics teacher how this is possible. The teacher tells him that is Mpemba's physics, not the universal physics. But here is the thing. Aristotle wrote the same observation down 2,300 years earlier. Can hot water really freeze faster than cold? In 1969, Mpemba and the physicist Osborne published it in a paper titled simply Cool? 70 milliliters of water, a small beaker, sitting on foam in a freezer. They varied the starting temperature and timed how long it took to begin freezing. The slowest to freeze was not the coldest sample. It was lukewarm water, around 25 degrees. Both hotter and colder water froze faster. So people proposed mechanisms. Hot water evaporates, leaving less to freeze. Hot water convects, carrying heat to the surface. Hot water holds less dissolved gas. Hot water might supercool less before ice forms. Every explanation sounded reasonable. None of them quite closed the case. Then, in 2016, came the careful version. Burridge and Linden ran the experiment under real controls, and they could not reproduce it. Worse, they found the culprit. Hot water convects violently, so its temperature is not one number. It is hotter at the top, cooler at the bottom. So the result depends on exactly where you put the thermometer. Move the probe a few centimeters, and you can flip which cup appears to win. And there is a deeper trap. The time to cool to 0 degrees is not the same as the time to actually freeze, because freezing is ruled by random supercooling. Under clean measurement, the kitchen effect mostly dissolves. As a law, hot water freezes faster is, honestly, a myth. But do not leave yet, because Mpemba's question, by accident, pointed at something deep and completely real. So forget water. Forget ice. Ask the abstract version. Two systems are relaxing toward the exact same final state. One starts close to the goal. One starts far away. Must the close one always arrive first? The answer, provably, is no. It is called anomalous relaxation, and the math behind it is gorgeous. Here is the idea. When a system settles toward equilibrium, its state is a sum of decaying patterns, called modes. Each mode fades at its own rate. There is always a slowest mode, the one that takes longest to die away. Wait long enough, and the slowest mode is the only thing left. So the real question is not how far you start from equilibrium. It is how much of that slowest mode you happen to carry. And this is the twist. A hotter starting state can carry less of the slow mode than a colder one. It loads itself into the fast modes instead. Watch two states relax. The cold one starts closer, but it is stuck in the slow lane. The hot one starts farther, skips the slow mode, and overtakes it. Distance from the goal and time to the goal are not the same thing. And this is not hand-waving. In 2020, in the journal Nature, Kumar and Bachofer trapped a single microscopic particle in a double well, cooled it, and watched a hotter state reach equilibrium exponentially faster than a cooler one. Exactly as the theory predicted. Tune the star just right, so it carries 0 of the slow mode, and you get the strong Mpemba effect faster still. The same anomaly now shows up in granular gases, in spin glasses, even in quantum systems. The water version is shaky. The underlying physics is rock solid. So the real lesson was never about water. It is this. How far you are from a goal is not the same as how long it takes to reach it. What matters is the direction you set out in and which slow traps you avoid. A system that starts behind can still finish first. Mpemba's frozen ice cream was probably a measurement fluke, but a 13-year-old with a stubborn question forced physics to discover that being farther away can mean arriving sooner. If this surprised you, hit like and subscribe. Counterintuitive science every week.